طيب يا شباب بسم الله الرحمن الرحيم. So last time we finished chapter 5 which introduced the second law of thermodynamics, and also we said we talked about the different results of the second law of thermodynamics, including determining the maximum performance of cycles, like a power cycle or refrigeration and heat pump cycles. And we gave an example of such ideal cycle or theoretical cycle, and we said the Carnot cycle is an ideal or reversible cycle that consists of 4 internally reversible processes. Okay, so this is quickly what we have talked about in the previous class and previous chapter. Today, inshallah, shabab, we'll introduce chapter 6, which it focuses on entropy as a property, so chapter 6, and how we use entropy in our analysis, okay? So using entropy. Okay. Before we go, do you have any questions about previous chapter? Any questions? No questions? Okay. All right. So let's see what we have here. Just a reminder of the second law, the Clausius inequality representation of the second law. What does it say? So this is second law. The Clausius inequality. Okay, so just a reminder, the Clausius inequality states that the integral across the cycle and the boundary, when evaluated when evaluated over the boundary and the entire cycle of dq divided by temperature across the boundary is less than or equal to 0. Okay, and we said this is equals to minus sigma of the cycle, and we call this the strength of the cycle, and we said the strength equals to 0. If the strength equal to 0, that means this is reversible cycle. If sigma is greater than 0, this is irreversible cycle. And if sigma is less than 0, this is an impossible cycle. Okay. What I would like to mention here now is that this integral here, what I'm gonna show you or what I'm gonna prove to you is that this integral here, the integral is a property. Is a property, and its change in value does not depend on the process. Okay, so if you remember, when we introduced properties, we said the properties do not depend on the process. Its value depends on the end points, right? So its change in value does not depend on the process. Depend on the process. Let's prove that. Let's prove that in a simple way. شباب معي؟ Are you following?
معك يا دكتور.
معك.
الحين احنا وش قاعدين نقول؟ قاعدين نقول انه الclasses inequality, this is the classes inequality. الآن I want to prove that this integral is basically a property. Okay? So, proof. طيب. To prove that, let us look at two different cycles. They share the same end states. Okay? So let's say I have state 1 here. This is state 1. And this is here state 2. Okay? And let's assume we have two different processes or cycles. Okay? Cycle 1 is you have process A here. Okay? And then goes back to 1. So this is a cycle now. I'll call this process C. Okay? And the second cycle is you have here process B, and then the same process C goes back to 1. Okay? So we have, so assume we have two. Now I'm gonna assume these cycles are reversible, two reversible cycles. Okay? So I'm gonna assume these are two reversible cycles. All right? So we have cycle A, C, and then the second cycle is cycle BC. Okay? معي شباب? So these are two reversible cycles. They start and end from the same point, and they also go to the same end. So from state 1 and state 2 are the same for both cycles. Okay? All right. Now let's look at process or cycle for cycle AC. Let's look at that. Let's look at the integral. Let's try to evaluate the integral here. Integral of dq by t. Hi Shabab, what's gonna be the integral evaluated? I want to evaluate the integral for all processes for all for the cycle. What do you think is gonna equal to? Hi Shabab.
Q at 0.1 over T1.
So for the cycle is from state 1 back to state 1 for the whole cycle. So it's gonna equal to from state 1 to state 2, right?
Yes.
dq by t for process. Now this is for process what? This is process A plus the integral from state 2 back to state 1 dq by t for process C. طيب, these are two reversible cycles يا شباب. What does that mean? That means the integral for the cycle, if this is equal to minus sigma of a cycle, it means what's equal to the sigma equals to what? If this is a reversible cycle,
It will be positive.
let's go back here.
It will be zero.
It will be zero. So
yes.
This is zero because these are reversible. So this is a reversible cycle. Okay, so if this equals to 0, that means the integral from 1 to 2 dq by t, okay, for cycle A is equal to minus, right, 2 to 1, 2 to 1 dq by t of cycle C. So this is for the first cycle. Let's look at the second cycle for cycle B to C. Okay, let's look at the same thing. For the second cycle, يا شباب, it's gonna be exactly the same thing. So from the cycle B to C, we have 1 to 2 for process B plus 2 to 1 process C, right? So eventually, what do I have? I have 1 to 2 process B is equal to minus 2 to 1 dq by T of process C. Do you agree with me, ya shabab? Because process cycle B to C is also a reversible cycle, so the sigma is equal to 0, and then eventually the integral for process B equals to minus integral 2 to 1 process C. Okay? طيب يا شباب, if you look at to these terms here and here, what does it say? If process integral for process A equals minus the integral of process C, and process B is also minus integral process C, it means also that the integral 1 to 2 dq by T for process A is
equals to
dq over T for process B. Okay, so you see that the integral did not change. The integral did not change, which means it does not depend on the process, but it depends only in the end states, which is state 1 and state 2. Is this clear يا شباب? Is this clear?
جدا واضح.
واضح.
Okay, so this is important. So since now we know that this is a property, so this we can write this down. Therefore, the value of the integral okay 1 to 2 dq over t between any two states, between any two states, okay, is the same regardless of the process. It's the same regardless of the process. Okay, so in this case, we conclude that this integral is a property. But since it's a property, let's give it a symbol. Okay, so we will give this symbol as, since this is the change between two states, we'll call it S2 minus S1 equals integral from 1 to 2 dq by t, and we're going to call this what? We're going to call this change in entropy. Okay, so S here, capital S, is just the extensive property of the entropy. So S2 minus S1 is basically this integral of dq over t. Okay, so if we take this in terms of integral also, we can have it at like ds equals, or if we um, yes, if we differentiate, right? So basically ds equal dq over t. Any questions here? So this is يا شباب
يا
the
دكتور
basic. Yes,
الاس وش هي هذه؟
الانتروبي.
يعني الانتروبي نضربه بالهيت بعدين نقسمه على
هذا الديفينيشن حق الانتروبي الحين.
اوكي.
الحين we just defined the، احنا وش قلنا؟ احنا اثبتنا ان الانتجرال هذا is a property. Okay, خلاص we will call this property entropy.
اوكي.
مظبوط. And because now if you integrate here you will get this back, right? Right? So if
Yes.
you integrate this, you get this back. So basically we're just rewriting in this form يعني. All right, so and this tells us, or this gives us basically the definition, the basic definition for the entropy, which is ds equals dq over t. So this is the original definition of the change in entropy. So this is the change in entropy, and this is the definition for it. So this is, since this is a property, and so it goes exactly the same as all other properties we have studied. So S here is extensive, is capital. So if I want to have the specific entropy, what do I do? Specific entropy is basically small s is capital S divided by, okay, so capital S divided by the mass. This is the specific entropy. But what about if I have saturated water or saturated mixture مثلا? You have saturated water mixture and you want to evaluate the specific entropy. It's gonna be exactly the same as before. You have SF plus quality times SFG, okay, or SG minus SF. So everything يا شباب we studied that applied to all other properties like specific volume, enthalpy, internal energy is also valid here. Okay? Right? So exactly the same thing. Also what we talked, if you remember يا شباب, compressed liquid صح? If you want to approximate the compressed liquid data, what do you approximate it with? If you have liquid, for example water, and you don't have compressed liquid.
At the temperature.
Saturated.
Exactly. So it's saturated liquid at certain temperature. So S at the temperature and pressure, for example, is approximated as the saturated liquid property. Saturated liquid property at the temperature. So this is for compressed liquid. So everything يا شباب we studied also applies to the basically the entropy here. Also, as above, if you remember, we studied TV diagram, PV diagram, right? We have also diagrams that can be used for entropy, like TS and
ابي المشاهد.
المايك يا شباب، المايك.
تسلم.
المايك يا شباب is open. TS and HS, okay? So we can use also diagrams or figures to evaluate properties or look at the entropy, okay, as a property. Any questions so far? Any questions? Any questions so far? Okay. So just a recap here. We proved that this integral is a property, and we're going to call this integral change in entropy. So we're going to define it as ds equal dq over t, and s here is capital S is extensive property, which is the entropy. Small s is the specific entropy, which is capital S divided by m, and then we can evaluate the entropy using tables, using figures, using equations, etc. Okay, so we're gonna look into all of these as about different equations. What's the entropy equation for, let's say, incompressible substances, for ideal gas and polytropic. All of this we're gonna look at. Okay, similar to what we have looked at before for other, for example, for internal energy or specific internal energy. And then after this, ya shabab, we're going to look into the entropy balance for closed system and the entropy balance for open system. And that should conclude يعني our chapter. يعني أنا أعطيتكم summary سريع على what are we going to do. Okay. Any questions so far? Before I move. Yes.
الحين الدي هذه اللي قبل الكيو تفرق عن الدي اللي على اليسار. شوفها اللي حاطها محددة أنت في المربع.
هذه البارشل دي وهذه الدي العادية، لأنه الكيو doesn't depend only on temperature، يعني have other properties.
تمام.
Okay, any other question? Any other question? Okay, so let's let's now get into the entropy equations. Okay, there are many, not many, sorry, there are important equations that can be used to evaluate the entropy. Okay, and these equations are the basis for the evaluating entropy, يا شباب. يعني when scientists try to and researchers try to evaluate entropy mathematically, they use these equations. So let's look at these different equations for entropy. So let's call entropy equations. Okay. So what are these equations? Let us start with the last equation we defined, okay, which is ds equals to dq by t, okay. So I can rewrite this as t ds equals to tq. Do you agree? This is good?
Yes.
Okay. طيب, for pure simple compressible system, if we write the energy balance, so the energy balance for pure simple compressible system, okay. Do you remember what's the energy balance for this? Shabab? Neglecting kinetic energy and potential energy. So I can write it as du equals dq minus dw. صح? This is a closed system, yes. Pure simple compressible system, okay. I didn't add system here. Okay, it's du equal dq minus dw. So I'm gonna write it in differential form. Okay. طيب, so that means I can rewrite my dq as du plus dw. Okay, so and also what's the equation يا شباب for the dw? Let's say we have expansion or compression. Do you remember the equation?
B delta V.
TdV, صح?
Yes.
TdV. Okay, so let's take this. Now I have TdS equals to dq. Let's take out dq here. So TdS equals du plus dw. And what is dw? Is P. So this is the first, we call it TdS equation. So these are TdS equation. Right? So this is the first TdS entropy equation. We remove the the Q, we put this one here, and then we also remove dq and pdv, and this is our first TdS equation. Can we derive another TdS equation? Yes. Using what? Using enthalpy. How? We know that enthalpy is equal to internal energy plus
PV.
PV. صح? طيب, if I want
Yes.
to differentiate this one, so I have dH equals du plus الحين PV, think of it as differentiation of two functions. Okay, so you have P dV plus V dP. All right, is this okay يا شباب?
Yes.
So we're just differentiating. dH equal du plus الأولى في المشتقة الأولى في الثانية زائد المشتقة الثانية أو الثانية في مشتقة الأولى. Okay, so this is simple calculus. So we got dH. That means I can remove du equals, so I can remove du and put dH minus pdv minus vdp. Okay, so let's do that. Let's take this TdS equation. So we have TdS equals, now let's remove du and put dH minus pdv minus vdp. Let's continue plus pdv, which is from this original TdS equation, plus pdv. What do you notice here? We can cancel what? pdv with
PDV.
pdv. This will cancel. So you're left with the second TdS equation, which is TdS equals to TH minus VdP. Okay, so we have two TdS equations. One is in terms of the internal energy, and the second is in terms of the the enthalpy. Okay, so one as a function of entropy, which is this one, TdS equal du plus pdv. The second TdS equal dH minus vdp. Okay, so these two important equations, which are the basis for evaluating entropy. Okay, so if you want to evaluate entropy, it will all depend on this equation. All right. So طيب questions.
يا دكتور
Yes.
الاستخدام يعني حسب المعطيات بس ما في قوانين ثانية، حسب المتوفر عندي بعوض.
يعني احنا انت عارف انه يعني في evaluating properties what we were trying to do if you remember we are trying to find the relations between properties صح؟ يعني زي مثلا حتى زي ال compressibility factor يعطيك property relationship ideal gas الفيجرز اللي هو الدايجرام الدوم مع ال temperature pressure specific volume all of this we're trying to find relations. Now these two equations give you relationships also to different properties. في الايكويشن الاولى بتعطيك relationship مع الانترنال energy والاذر properties اللي هو pressure volume والtemperature. الايكويشن الثانيه لا بتعطيك البريشر فوليوم تمبريتشر مع الانثالبي مش مع الانترنال انرجي. ليش؟ لانه الانثالبي والانترنال انرجي are related. Okay, this is the idea. So it's just basically a relationship. So you are right, and it depends on what you are given. You can proceed. Use which one يعني suitable. But the general idea is that these give you relationships between different properties. Okay. Yeah. Good. Okay. So if you notice these equations, I wrote them in terms of the extensive property. So if we want to write it in terms of intensive properties, which is let's say per unit mass, so we can write TdS per unit mass. So what's it gonna be? It's gonna be T small s equals D small u plus P D small d. So if you divide by m everywhere, and left hand side or right hand side, you get this equation. Also, يا شباب, if you remember, we can write it per unit mole. You divide by number of moles, okay? You get the molar form, which is ds bar. If you remember, we put a bar. That means this is per unit mole. Actually, let me write the second ds equation here. Equals dH minus specific volume times dP. Now this is per unit mole. It's going to be the same except that this is a molar form plus P EV molar. The same thing for the other equation. Okay, so these are the two equations, each for different representation. One is per unit mass, one is per unit mole. I wrote this wrong here. This is mole. Okay. طيب, let's see what's the, for example, يعني as an example, for a phase change, from saturated liquid, which is F, to saturated vapor, G, okay, what would be the property, for example? So if we apply, for example, TdS equals dH minus, انتم عارفين يا شباب انه from F to G, usually let's say let's say in an open, you have no external factors, مثلا زي spring or مثلا a force pushing changing the volume or the pressure. So we usually you have let's say water like this is boiling. Okay, so it's from saturated liquid to saturated vapor. So this is a constant what? Constant temperature and pressure, صح? Okay, so the phase change is usually constant temperature and pressure. So if we apply the equation here, TdS equals dH, we're gonna pick this one. Why?
The pressure is the same.
Because the pressure is the same, so I can cancel this term. So it's minus V dP. So since the pressure is the same, so I can cancel this one. And the final equation becomes TdS equals dH. So ds equals dH over T, and also our temperature is constant. Therefore, Sg, if we now integrate, Sg minus Sf equals what? Hg minus Hf divided by T. If you go يا شباب to the tables, okay, and go to any temperature, for example, in a phase change, if you take the difference of the enthalpy and divide it by temperature, you will get the change of the entropy. So you can double check your calculation. Okay, so this is how the entropy is calculated, even in the tables. Okay, this is how it is evaluated. وضحت الفكرة يا شباب؟ Is that clear?
ايوه دكتور.
So this is just an example to show you that how we can use the this relationship for the entropy or the TdS equation to evaluate the entropy. I guess we can talk about this quickly. Yeah, we can talk about this in this last 5 minutes. So also we have the entropy change for incompressible substance. Okay, let's see how the entropy change for incompressible substance. If you remember, يا شباب, when did we call the substance incompressible? What was the condition for incompressible substance? We said the specific volume or density. شباب ما تذكرون. These are basic concepts. لما تسمع incompressible يعني غير قابل للضغط.
liquid يكون هو solid اللي هو
مو شرط liquid or solid. احنا نتكلم incompressible. When do we call the substance incompressible? يعني أعطيتكم هنا إنه specific volume or density
when the specific volume is constant.
وشو؟
When the volume is constant.
مو الفوليوم.
Specific
volume ولا density؟ احنا وش قلنا؟ كيف constant كذا بس؟ It does not depend on, so it does not change with. شباب.
time.
ترى أعطيكم F كلكم.
نشارك كذا. والله ما أدري.
الحين تحمستوا.
Doesn't change with time.
خفنا.
يا شباب فكروا في الكمبرسبيلتي. ايش يعني كومبريسبل؟ انا قاعد اقول لكم بالعربي غير قابل للضبط. يعني ايش اكثر من كذا يعني؟
البوندري doesn't change.
Specific volume doesn't change with time.
ما يتغير مع الضغط.
قلت بريشر طيب.
ايه سمعتك. Okay, so it's constant with pressure, so it does not change with pressure. Okay, in this case, the properties usually is a function of what we said is a function of temperature only. Okay, is a function of temperature only. So in this case, يا شباب, our specific volume and density are constant, and the property will also change with. The properties will only change with temperature. The same thing we can apply to the entropy. Okay, so the entropy. So we have TdS equals. Let's write the equation is du plus PdV, right? And since the properties are a function of temperature, we know that du is what? Using the specific heat is C as a function of temperature dt. Okay, so this is the original definition for the du. Alright? So now we have this equation for the entropy. What is dV here?
Zero.
ليش؟
Zero.
Constant with pressure.
Constant volume.
It's a
Constant.
constant volume. So this is 0. So basically TdS equals du. That means ds equals du over t, or I can rewrite it as c t tt over t. Okay, so if this is okay. If I integrate, I get s2 minus s1 equals integral of c t dt over t. Okay, this is the equation now, so let me put it in square. This is the entropy change for incompressible substance. So if you have incompressible substance, this is the equation you can use to evaluate your change in entropy. طيب إذا C constant اللي هو specific heat, إذا C constant, what's the result? If T is constant, شباب C بتطلع برا خلاص. D over T is what? وش الانتجرال حق 1 over T dt؟ ما. So we have C ln 2 over T. ايش فيكم يا شباب؟ نسيتم الماث ولا ايش السالفة؟ Okay. So this is the final equation if the C is constant here. Okay. So this was quickly the change in entropy for the incompressible substance. Okay. Next class we'll continue. We'll talk about the change in entropy for ideal gas. Okay. And for variable specific heat, for constant specific heat, and then we'll talk about also for reversible, internal reversible of closed systems, okay, and so on. Any questions? Any questions here?
No.
يلا يا شباب كملوا نوم، واضح نايمين. يلا. Take care.